up, athletes? Whoop, whoop. All right, this is 3.5, Shapes of Graphs. I will identify extrema and end behavior of functions. Go ahead, take a minute, read A, B, and C, and answer about these graphs. Ready, set, go. Okay, I'm assuming you've paused this, as I will throughout the video. Write stuff down, and then we will boot, scoop, boogie. Okay, the distance between A and B on Jamal's graph is constant. What does that mean? That means Jamal didn't move during this time. So Jamal didn't move during this time. Sophia's graph goes up more steeply than Jamal or Aaron's. What does this mean? She was moving faster. Right? If it's distance over time, it's steeper. It means she's going a faster distance over the same amount of time. She was moving faster. Describe Aaron's trip. Well, from A to C. So from A to C. Aaron traveled at a constant rate. Okay? See how he just went the same speed the whole time? As long as you said something about he went the same speed the whole time, he just kept moving, that's fine. Okay, we got some vocab to get through. Let's do it. We have line symmetry. A figure has line symmetry if each half of the figure matches the other half exactly. We'll talk more about that, but basically, if I can put a line down it such that it cuts it exactly in half, it has line symmetry. Increasing, it's increasing where it goes up from left to right, and it's decreasing when it goes down from left to right. The extrema are points of locations of relatively high or low function values. I call them the mountaintops and the valleys. And the end behavior is the behavior of the graph at the positive and negative side extremes in its domains. This all sounds a lot more complicated than it is. We're going to get into it. Okay, pause this as needed. We're moving on. Wrong button. There we go. Okay, so let me move myself back up where I normally am at. We're going to talk about symmetry in graphs. Symmetry of graphs of functions. Okay, when that symmetry is in the y-axis. In the y-axis. Let's look at that. I'm going to get out my little triangle ruler to help me as I go. But when it's in the y-axis, boom, so here's the y-axis right here, right? When we have symmetry in that, that means if I were to cut, this is a parabola right here, it's called a parabola. Okay? P-A-R-A-B-O-L-A. Okay? So it's a parabola. If I were to cut it in half right here, this side, here, I'll highlight it, make it a little easier to see. This left half would perfectly match up to this right half. That's what it means to have line symmetry. And by the way, this is called the line of symmetry. Line of symmetry. Right here that I drew, okay? And we usually shorten that to L-O-S. So if you ever hear me say L-O-S, that's the line of symmetry, okay? How about a vertical line other than the y-axis? Vertical line other than the y-axis. Well, in this case, look at this graph, this W. Can you guys see where I might draw a nice line that would cut it in half so that I could fold it over on itself? Yeah, right here. I normally do a line of symmetry with a dotted line, dotted or dashed. So again, this is my LOS, and it's at, what is that x value right there? That's x equals -1, okay? Because we see it's just 1 back from the y-axis. But again, let me highlight it so you can see it a little easier. This would fold exactly over onto itself right here, okay? Those are the same exact, those halves are identical, they're symmetry. Now let's look at the last case. Now this is not a function, guys. These two are functions, this is not, because no matter where I draw that vertical line, except for at the very end over here, it's going to hit twice. However, there is a symmetry here, and that symmetry is in the x-axis. Again, not a function. But we can see there is a symmetry right there, right? If I were to turn this to the side, it's in the x-axis, right? And that would be my symmetry at, what's the value of y right here? So that's the line of symmetry at y equals 0. Okay? That's symmetry in the x-axis, and we see that because, again, it cuts this perfectly. I just realized you can't necessarily see all that. It cuts it perfectly in half. Boom. Good times. Okay, it says use the following graphs to describe the line of symmetry of each function if one exists. Go ahead, look at this one right here. See if you can draw in its... Man, I keep describing stuff you're not seeing. Let's look at 1A. See if you can draw in its line of symmetry. Pause this if you need to. Ready, set, go. Okay, looking at it, it looks like it's going to be right here at 4. And again, that's LOS is x equals 4. Okay? If I were to fold that over, boom, it would be exact. But what about right here? Look at this one. What's going on there? Is that going to work? Is there anywhere I could draw a line? Right? Even imagine this being the line. Kind of looks like right there, but even then I wouldn't. This is exponential. There's no line I can draw that's going to work right here. So this one has no line of symmetry. Line of symmetry. And as I draw this, it hits me. Why didn't I just say no, LOS? Don't know why I didn't do that. Okay? Now we're going to take a minute. We're going to look at a slide. So there we go. Let's take a look at this fountain. Does everybody see that fountain? See how it's starting up here and it's making a nice little parabola going down right there. All right. So let's go back and look at what we have right here. It says a fountain is spraying a stream of water up into the air. We just saw that. We can still even hear it. You can annoyingly hear it. Boom, let's stop that. See how that looks just like the graph you should be looking at on your paper? Okay. Fountain spraying a stream of water into the air. The graph represents the path of the water, where x is the distance from the fountain, and y is the height in feet of the stream. So let's go ahead and fill that in. So it says x is distance from fountain. Distance from fountain. And the y is the height in feet of the stream. So the height of stream. And again, we're told it's in feet. Okay, so let's look at that. Find and interpret the symmetry of the graph of the function. Okay, let's go ahead and do that. Now, this may not be in the way you're normally used to looking at it, but I think we can all see that the highest point is right about here. That's where it's going to get cut in half. So let's draw on our line of symmetry. This is my LOS, and it's at what? X equals 2. Okay? 2 feet, really, because it's 2 feet from the fountain. Okay? And what does this tell us? Well, I want you to look. Notice that every one of these is going about 2, 4, 6. So this middle point right here, so it's really passing through right about 4 feet right there. And we see that it's going to hit right about 4 feet here. I know I'm estimating a little bit, but we're just going to say right about 4 feet. So if I were to connect that line, do you see that? That tells me from 0 to 2 feet. So from 0 to 2 feet right here. From 0 to 2 feet. The height of the fountain goes from what? Goes from 4 feet in height right here to about 9 feet in height. That's just halfway through to 9 feet. Okay? What else do we see? If we go from 2 feet to 4 feet away, so from 2 to 4 feet, the height of the fountain goes from 9 feet to 4 feet. So it goes back to the same of where it started, okay? And we can see if we go past that, then it's going to go down to ground level or water level like we saw in that fountain. Yeah. Boom. All right. Let's go to the back.